So with this chapter, we've been talking about energy. So electric potential energy. That is our U. I'm going to put a subscriptive E. We don't need a subscript per se, but the potential energy, a point charge, is specifically what we've been talking about. The electric potential energy a point charge has because it's nearby some other charge. Whether that charge is another point charge, not squared. Oh, that's going to be a common mistake, by the way. We're so used to having r squared in the denominator from force and electric field that it becomes kind of second nature to square that. But when we derived this, the square, of course, is gone from integration. So this equation is specifically the energy Q has because it's near capital Q. So I've just been using a lowercase q to represent the charge that feels the force or that has the energy, and capital Q to represent the charge causing the force or creating the electric field. So this equation is specific to this particular situation. Earlier, we found also in a specific situation that we could write the energy. Oh, come on. Sorry, my computer is rebelling on me. The potential energy a point charge has because it's between the plates of a capacitor. I guess I should specify a charged capacitor. It's in the electric field of the capacitor. This is only specific to this situation. It can work actually for any uniform electric field. If we know we have a situation where we have a uniform electric field, it can simplify to this situation where S is specifically defined as 0 at the lowest possible potential energy location. Generically, we can say the energy, the potential energy a point charge has, is determined by its own charge times what we call the electric potential, which we've been talking about in previous videos. Now, just another word of warning. Electric potential energy versus electric potential. Without the word energy, we mean V. We mean just how another charge is influencing the region of space around it. Electric potential relates to where in an electric field we're talking about and putting this charge Q. Okay, so let's go back to the example with a capacitor for just a second. Just because we've already been talking about that. A capacitor is defined as having these two plates, also called electrodes, one being positively charged, one being negatively charged, with the same surface charge density. The electric field between the plates points from positive to negative. When we talk about the electric potential, we're talking about locations where we can place a charge and it would have the same amount of energy. That's those equipotential surfaces we were talking about. Inside the capacitor, it's a line and essentially a plane parallel to the charged plane. This potential V2, I'm only drawing 3 potential surfaces, but essentially the potential varies linearly as we move from the positive plate to the negative plate. And again, when we derived this equation for potential energy, we defined the negative plate as S equals 0. And so in our equation, S simply represents where we are measuring from that negative plate. So for example, S1 would be from the negative plate to where I drew that equipotential surface, V1. S2 would be from the plate to where V2 is. So in this equation, S, that's what we mean by S, the distance from the negative plate. Now, if I take a charge, let's say I put it right here in the middle, on top of V2, and released it. We're not going to worry about the logistics of doing something like that. But if I were to place a positive charge in here and just let go, we know it's repelled from the positive plate and attracted to the negative plate. So we know it will move to the right. We've already looked at problems in this previous section where we knew the force was Q times E. We could find acceleration. We could find speed, knowing distance or time. Here, we're going to talk about energy. The amount of energy our charge has, at that moment in time depends upon its charge, Q, and the V2 that I put it at. Just using this equation. The potential energy depends upon its charge and that potential value. This charge I'm releasing from rest. So the total energy initially, and technically this is called the total mechanical energy. Mechanical energy. It's all potential energy right now. Well, conservation of energy, we know the total mechanical energy initially has to still be mechanical finally if there's no non-conservative forces like friction or drag, which neither of those come into play in this particular situation. So depending upon where we're talking about as our final location, say we want to know how fast the charge is going, here, this is our final location. Well, our charge is at a location where we have V3, so there is still some potential energy, but it is also moving. Now, we do want to be careful. Make sure we're distinguishing between speed, because kinetic energy, 1/2 mv squared, that v is how fast, and then potential, or volts. we could find this final speed Sorry, there's still a lag. My computer's working hard in the background. We could totally find this final speed by knowing these two values of electric potential or voltage that the charge has moved through. Knowing the charge and the mass of the charge, we can get to speed. Okay, since point 2 is my initial point and point 3 is my final point, I have here a Q times a V initial minus V final equaling R 1/2 M V squared. When we talk about delta V, that specifically means final minus initial. So we actually have the opposite of delta V right here. Come on. So we end up seeing negative Q delta V is equal to the 1/2 M speed final squared. We can relate the motion of our charge to simply the potential difference it moves through, which is really cool. Now, this equation is not quite complete. We assumed the charge was released from rest, so it's totally valid in that situation. But if it's not released from rest, our equation, this negative Q delta V, let me try to write that better, negative Q delta V. If we had an initial speed, we would have had to bring the initial kinetic energy to the other side. Which, fine. This relationship works wonderfully to analyze the motion of a point charge moving through an electric potential difference. Electric potential difference is that delta V. Now, by the way, the Q delta V represents the change in potential energy. Right? If we come back to this equation on the left, if the potential energy is Q times V, then the change in potential energy is Q times delta V, because the charge isn't changing. And then that is equal to delta K, which is just another way of writing out this conservation of energy. It's the same thing. But this gives us a really nice way to relate potential difference to speed. And it doesn't matter in this form it doesn't matter if the electric field is uniform. To use this in terms of delta V. What we would not be able to do, sorry for moving stuff around on you so much, is use these equations up here for potential energy if we did not have the specific situations that we described them for. If you know the potential difference, regardless of what's creating it, we can relate that to the change in kinetic energy, which is very nice. I'll do an example in just a minute in a separate video. I do want to talk about one more potential energy, and that's the potential energy of an electric dipole. Excuse me. If you recall, an electric dipole is when we have an equal and opposite charge. So they're the same magnitude, but one's positive, one is negative. We get a dipole moment, P, this electric dipole moment. The magnitude is Q times S, where S is specifically the distance between these two. The direction of the electric dipole is negative to positive. It's opposite the electric field. If I take this electric dipole and it's in a region that has an electric field created by something else. So these lines I'm drawing now represent an electric field created by something else. I don't even care what's creating it. I know this electric dipole I drew is not going to stay in that orientation. In the last chapter, we talked about the torque. Torque is the dipole moment crossed with the electric field. Torque meaning a twist, a moment. It's going to turn. In this particular case, this will turn this way. Maybe I should use a different color. Orange. So this way, because this positive charge is attracted to whatever is negative in terms of creating the field. So the positive charge wants to get towards the negative, and the negative will rotate towards the positive. So this dipole ultimately will rotate in hopes of lining up. Not that it really truly has hopes, I know. But it ultimately is going to line up with that electric field. So there was a torque or a twist because of its original orientation. Well, the fact that it's going to move means it also has potential energy. That potential energy will turn into kinetic energy as it starts to rotate. The equation to calculate the potential energy of the dipole moment in this electric field is negative P, the dipole moment, dotted with the electric field. We can write any dot product equation as the magnitude of the two vectors times the cosine of the angle between them. So coming up to my picture, I would draw E and P at the same place. Theta is specifically this angle between the electric dipole moment vector and the electric field vector. With our angle in my picture being greater than 90 degrees, the cosine of theta is going to be negative, meaning this has a positive potential energy. as it rotates, as the dipole moment rotates, the absolute lineup here, when P is lined up perfectly with E, theta in this case would be 0. But that doesn't mean 0 potential energy, right? Our equation, negative PE cosine of 0 degrees is 1. The potential energy when it's completely lined up is the most negative it can possibly be. Meaning this is the smallest possible potential energy of the dipole. Now, as it rotates, its potential energy will turn into kinetic energy. It would specifically be rotational kinetic energy. So that potential energy would be turning into K rotational, which we're not going to solve any problems using this. So if you're currently using the night book, that's what I'm making the videos for. We are not going to use rotational kinetic energy. But I wanted to mention that. So potential energy will still totally turn into kinetic and back to potential. So if there's no forces to take mechanical energy out of this system, this dipole would theoretically just rotate back and forth, kind of like a mass on a spring. In an ideal situation with a mass on a spring, where it would oscillate forever, so would this dipole. But its oscillations would be rotating around its center of mass. Okay. So this equation is what we're getting at for the electric dipole. I'm going to go through and do a couple examples talking about motion of a charge in an electric field and potential as well.